Thank you for coming, everyone. Let's talk about some interesting developments that I think we are sort of reliving through. So I want to sort of go through the historical developments in space science and how there are a lot of distinct parallels between what is happening now in data science to what happened long ago in space science, and how we sort of surmised models from data and how we went about it. So I'm going to do a brief history of celestial mechanics. In the process. Of course, we know from like the plans, it all began with as most of you know, Copernicus started and he proposed the heliocentric model that sort of kicked off everything. There were two sets of astronomers after Copernicus. One of them sort of, most of them before Galileo, and that's why Galileo is so important, used just, sextants, so just, observations from an angle type instrument to record the celestial observations and mainly planets. Of course, people started from a much prior time to Copernicus. They knew the distinction between planets and stars. And based on that distinction, planets were moving a lot faster than stars were, and sort of where they were able to they were trying to understand how Earth is situated in relation to the planets and stars, and mainly the planets, and then how planets are moving around. Most important planet obviously was Mars, and Mars comes back later in our discussion. So this is sort of a drawing of how the world, how the cosmos was, and then that was essentially the cosmos that people used before Copernicus, we have that was the model. Then Galileo devised this instrument called the telescope, and really observational astronomy and observational special mechanics was born. He really discovered most of three or four Jupiter's moons, and he wrote the treatise, which basically said sun was at the center of the universe. Of course, we all know how badly he was persecuted for this idea. So I think we all should learn from that and speak truth to power. Although you're speaking in low voices, you should still speak truth to power. Anyway, so modern times also probably will have instances in the future, so we have something to learn about that. In any event, Galileo really triggered a lot of interesting things. And even before Galileo introduced his astronomical instrument, the telescope, there was a guy, Tycho, who was a very colorful character, apparently. Of course, he's the descendant of some, aristocrat. So, but he also wanted, he claimed he was a self-professed expert in mathematics, so much so that he and his cousin had a drunken fight, and he lost his nose in the duel, essentially. So that is the colorful character Tycho, and of course he had many appointments. Initially, he also had many friends and girlfriends and so on and so forth. So he apparently fell in and out of favor of the local ruler for various interesting and colorful accusations. and so on, and we talk about a few of them. So what his main job eventually, after he lost his nose and he became a little too old for sword fights, he started managing an observatory in Prague. And that observatory was specialized in making measurements, and they were still making measurements using sextants. And Tycho, in all his adventure spirit, apparently was a very good mechanical engineer. And he would make, he recognized that the precision of his azimuth and elevation measurement of the planets was not enough. And he actually built big sextants. Some of them were as big as 6 to 7 foot. And this is a mechanical drawing of one of the sextants he built. And with those, he was able to make arc-second accuracy measurements of the azimuth and elevation, which is really unprecedented, very pristine. And some of those measurements are actually documented. So among the first accomplishments of Tycho was a star catalog. And most of us use star catalogs in aerospace engineering to record the inertial location of stars, and that's how spacecraft navigate themselves. And the origins of star catalog seems to be from Tycho and Kepler. They published the first star catalog version, or primitive star catalog version. So he also dabbled in alchemy. He wanted to make he really wanted to make measurements. So Tycho had the sextant, and then he himself was not a believer in heliocentric theory. He wanted Earth to be at the center of the universe, but his main contribution was he observed that there was a fixed star background. But then later on, and at that time, everybody almost universally believed that stars were immutable. They were fixed to some celestial, circle. They didn't think it was spherical, I guess. So they thought that there was a immutable, hemisphere or whatever they called, and all the planets were revolving around the Earth, including the sun. But then he confessed and basically allowed the moon to have an independent rotation about the sun. That was his main contribution. Anyway, now at the age of 54, which is relatively young for us, he dies of kidney failure. A year before his death, this young 30-year-old kid called Kepler starts a job with him. And of course, the rumor mill says, I don't know what MVP is, some audience person is saying MVP. Rumor mill has that, okay, 1 year later, this guy, killed Kepler for his data. Because later on, he uses the data to make the first model, right? And we all know Kepler's laws, and they were all to explain the data and so on and so forth. So basically, people thought for a very long time that he was murdered for the data. So much so that he was exhumed twice. Once he was exhumed in 2010, and these are some visuals from this person is very happy to hold Tycho's skull. It's very, I don't know, I found this extremely hilarious that, he's holding the skull and is very amused with it. And this is another visual of them, exhuming Kepler. I think that one is the second exhumation. The first exhumation concluded that Kepler died of mercury poisoning. That was in 2010. Then later on, there was another exhumation, I believe in 2012, 2 years later, they exhumed him again. And I'm sure, Tycho was having a lot of fun from wherever he's seeing all this. So then they found that he actually indeed his cause of death was actually kidney failure caused by heavy metal poisoning. They had a lot of gold remnants in his in various remains, including hair and so on and so forth. Apparently, they used to drink gold, and they used to mix gold with wine and drink that, and that's what was basically causing a lot of problems. And of course, they also he would make a lot of amalgams for his artificial nose was by the way metallic, and it was an amalgam. So he would actually mix it himself and engineer it, of course. And people now think that he probably poisoned himself. But apparently the local king was also not very happy, because his latest girlfriend was the king's mother. So they all thought that there were many people who can actually who's responsible for death of Tycho. For whatever the reason, obviously Tycho died, and we don't know exactly why, but it's clearly because of some, whatever, 15th century habit of devouring heavy metals. Then we basically end up with Kepler, and Kepler is not only he's obviously very hardworking. So he took the data, and he was really the first project he had was this Rudolphine table. From what I could read online, these tables were a primitive star catalog. They didn't have the modern system of storing them and measuring interstar angles and whatnot we do these days, but there was a very clear tabulation of the known stars at that time. He was the imperial mathematician, and of course Tycho was also the imperial mathematician. In those days, these imperial mathematicians, guess what their job is? More than crunching numbers and looking at stars. What is the closest discipline to astronomy?
Astrology.
Astrology, that's exactly right. So he was supposed to predict all these, what the when is the next warlord going to attack this, and when is the next, famine going to be, and so on and so forth. That was the main thing. So of course, they did that, like latest thing on, stock market type stuff is the astrology at that time. So that's what he did. Most of his day job, and then in the evening he wrote papers on explaining planetary motion. The first really good treatise is Astronomia Nova, New Astronomy, and he was the first who gave the first two laws of planetary motion, and actually showed that this is his illustration, by the way, in that book. He showed that to the reference circle, the Mars's data is this dashed line, which is compressed or squished, and he showed by computing areas in the triangles that equal areas, the areal velocity of Mars is constant about the sun. And he was a Copernican, so according to him, sun is at the center of the universe, and that's how everything sort of fell in place. And he has many excellent, narratives of how he could not exclude, and accordingly, apparently at that time, everybody was confusing religion and science. I guess even to this day, people do that. And they were all obsessed with fitting the planetary motions to circles. So ellipse was sort of unexplainable for them. And we are all, it is sort of, I think it's human nature, sort of get carried away with, beautiful, elegant expression. and then sort of not accept the fact that, oh, there is some mistake. It can't be this, ugly ellipse sort of a situation. And we see that all the time, even now. In my own work, when I go and derive some higher order terms or whatever, I used to double check or triple check or quintuple check if there was something that was out of place, and it's not quite in place, and so on. So that's I think, and of course, Kepler, like all of us, is a periodic freak. So he's such a freak that he wrote a book, Harmonices Mundi, and Harmonices Mundi is so interesting that it has a section on geometry. If you see, you can see that there is a spatial periodicities volume. There's an entire volume on spatial periodicities. There's an entire volume on notes and rhythms and harmonics in music. And then as a cursory note in volume 3, which talks about perfect ratios, he says, the maximum minimum speeds of planets are approximate to musical harmonies. Of course, some of them are exceptions, like Mars to Jupiter is 18 to 19, but most of them follow the ratios of speeds, and the ratios of speeds are integer numbers, and they're commensurate, and so on and so forth. The beautiful dynamical system theory would have actually, hopefully, he would have pleased Kepler as well, even in modern astrodynamics and astronomy. He had some concept of what kind of a force would basically cause this elliptical motion, but most of his studies were necessarily kinematic. He had to work with data directly. Now, there is a very strong correlation with some of the database modeling techniques we see these days, right? So people use RBFMs and a lot of networks of different types, their structures and forms, and then they work because they are like the data. So before Kepler, who explained this very clearly, there were many people who were just using the data to predict the next horrible death of the king because of some other comet or meteor and so on and so forth, meteor shower, whatever, right? That was a model as well, and I sort of draw a parallel between that and the simple models, the simple regression models we use these days blindly, because we want to get some work done. We cannot stop. We don't have, all of us don't have, positions like Kepler and Tycho. We are not aristocrats. So we cannot just keep banging our head and find that perfect description of data. Sometimes it's not possible. Sometimes we have to just move on and get some work done. So that is sort of the distinction I would like to bring to bear in this discussion. Some problems are waiting for their Kepler. Some problems never get their Kepler, of course, and so on and so forth. So that's an interesting point. But there is an elegance in waiting and not jumping to conclusion and just blindly going through, right? So as engineers, most of us have a tendency to just write a formula and move on. Sometimes it's useful to check in the neighborhood of a formula or in the neighborhood of a known description. If there is some deeper meaning, then it actually makes a larger impact. Then came, of course, the most profound modeling genius, Sir Isaac. Of course, I don't have to tell any of you how legendary Principia is, and how he sort of, we give Newton a lot of credit. He earns it, but of course, modern celestial mechanics was built not only by Newton, because calculus he invented, but his calculus was infinitesimal calculus. It's almost like finite differences we do these days. Without Leibniz, without Euler, we don't have the kind of derivative operations and integral calculus that we have today. So I think although Newton gave us answers from a different perspective. He gave us equations, nonlinear equations to solve for orbital motions. He gave us a constant. He actually hypothesized a constant. All those are very monumental contributions directly from data themselves. But there are a lot of other geniuses at work. One of them is Euler. Of course, Euler had his own celestial mechanics. He was obsessed with an asteroid a comet that he saw at that time, and he had his own version or interpretation of Sir Isaac's formulations to basically explain the periodic motion or predict the motion in time. And of course, Laplace's monumental contributions are actually very important because he took Newton's calculus and married them with Leibniz and actually did most of what we know today, a sort of Laplace's elements, and we honor him. We have a Laplace vector to honor him, and because he gave us that Laplace vector in some sense. So the most interesting thing, you can look this up. Google Books, Google eBooks have a free treatise of Mechanics Celeste, and Mechanics Celeste is a 5-volume text. I think it's very large. It has many contributions, and Laplace was the first person to depart from the point mass behavior of the primary body and the orbital body. He said the primary body does not have to have a point mass; it can have a mass distribution, and he derived an equation to represent the force gradient of that equation to give us a force experienced by the point mass that is orbiting a continuum body. And the most interesting feature of his entire textbook, I have actually looked at it a few times, at least the ones that were accessible 3-4 years ago when I looked at it last time. It has no picture, it has 0 pictures. It's entirely mathematical. And he thought it was a big work of art, because writing a text in celestial mechanics without an ellipse is first of all no mean feat, but also that is what you should not do. It becomes so inaccessible to the common populace that nobody uses Laplace. I mean, if I use Laplace as a textbook, I mean, I'm sure none of you would have taken my class. So that's a different kind of treatment. So I think we all have. I know, by the way, they might have been all these people whom we admire as heroes. They might have been shit people. I mean, they might not necessarily have good personalities. They may not have mentored, nice and so on and so forth. So I'm only admiring their genius, not necessarily their personal things. Sometimes they don't necessarily go hand in hand. And of course, we have the great Gauss. Data science cannot be, what it is without Sir Gauss. All of us, in some way, form, or kind, are related to him in terms of our technical ancestry. That is, if you got a PhD somewhere, or if you're studying with somebody, you are related to Gauss because he produced so many people. I have a joke about this. So he probably, so he did all this. He invented least squares. He found Ceres as a minor planet and all that stuff, and and so on. But his primary occupation was his work, theory of motors, theory of motion of celestial bodies. That's what that roughly translates to. And I'm pretty sure he had like hundreds and hundreds of people who were doing these Gauss elimination calculations for each iteration. So if you, he probably had like a room full of people taking, crunching numbers and giving the next iteration. Okay, are you done today? You know, in an hour, I need the next iteration. They would all go back and do it. And then each of them would get a PhD for each iteration, something like that. So probably, you know, because of that, he probably has so many students. And then, you know, his students then, you know, went on to invent more students and so on and so forth. I think that's why most of us are related to Gauss. That's a seal. But I think he was a perfectionist, and he would put this seal of approval. And if you see the seal, it's in Latin, it is a few but right. But I think he graduated a lot of students though. I don't know about this few but right thing. So he has this Foca said, Natura, there is a tree here, it has only 6 fruits, you know, and that's sort of the motto. But he, as you know, most of you know, he has contributions ranging from, you know, discrete mathematics to graph theory. You know, he put that Königsberg bridge problem, and of course we won't be able to do anything today without Gauss's equations. He basically invented the variation of parameters to solve the problem of perturbed motion, because he said, oh, all these people know how to solve the two-body problem. Let me go attack the next one, which is the presence of perturbations. And of course, he invented error analysis, probability theory. The Gaussian distribution is in his honor. And of course, the most important method of least squares, and also solving linear system of equations. Gaussian elimination is directly from Gauss. And I don't believe, you guys can correct me if I'm wrong, they sort of had matrices, but not really. But later on, the matrix theory was sort of more formally, you know, developed much later. But he was using a version of matrix theory that was not quite developed as rigorously as Gibbs and others developed later on, and that sort of the thing. Of course, Gauss gets a lot of credit, but there are a lot of other people who worked alongside and developed a lot of programs. So I'm going to skip some of those and go to the modern age. And now we can talk about things that people that are not that well published and well known. Of course, Russians launched Sputnik. And one of the most important contributions of US space scientists and related to data science is 2 weeks after Sputnik was launched, 2 scientists at NRL, Richard Underley and Klaus Osterwinter, estimated the Earth oblateness parameter to 2 digits, or 1083.93 is the coefficient times 10⁻⁴, of course. But they estimated it to one of the digits. They got the 1083 correct. That's an amazing accomplishment. They were just tracking the satellite that the Russians launched. It was supposed to be their activity is just intelligence. You know, they're just tracking this satellite. And based on that, then they developed their own satellite. It is GEOS-1. They launched 2 years later, which killed it, which took J2 and estimated it to 70. And that's one of the most important accomplishments of modern time. Of course, then Apollo era started, and many other things happened. But you know, in that, we don't give a lot of credit to Richard Anderley. Interestingly enough, I was trying to look for his technical note that they published at that time. I couldn't find any, but there was a NASA technical repository server had some data on GEOS-1, which actually documented that they were able to estimate the first harmonic coefficient of the Earth. And of course, we know a lot more now. We heard from Dr. Srinivas Vettadpur about GRACE, and GRACE is a sort of a modern marvel. GRACE has 2 satellites. that are basically in the same orbit, they are in tandem. And because of when they observe any gravitational anomaly, their distance changes because the lead satellite gets pulled by, let us say that's Mount Everest, it gets attracted by it, and following satellite sort of waits and experiences it later, so they become like a spring. So there is a gravitational spring, and you estimate the gravitational coefficients based on the ranging data between the two satellites, and the ranging data is very precise. So they are separated by 100 kilometers or so, but the ranging accuracy is about I believe tens of meters or something like that. And even then, you can determine the coefficients and very reliably. And of course, Earth, because of Grace data, is a dynamic object. It has now a time varying potential, and we can download the Grace harmonics and calculate the properties of the mass distribution of the Earth very reliably from this data. So it's a very interesting, it is, I think, a scientific contribution and a very important data problem. I mean, in this case, we are using actually Laplace's model of the gravitational, but I'll talk about that a little bit because we have recently worked on that problem. But it's a big data problem, and I'll talk about why it is such a big data problem in just a little bit. So I think the current Grace model is 6,000 by 6,000. I can't remember. So there are many coefficients of the model, and depending on whatever your desired accuracies, let's say if you want to know the accuracy of motion to a centimeter level, we need to use a very high order model, and vice versa. So let's talk a little bit about gravity and why it is a big data problem. The gravitational potential following Laplace is expanded using this formula. These are Legendre coefficients. They are called they are basically associate Legendre functions, and then the entire problem is then reduced to these harmonics C and S. And the key problem in gravitational modeling is that as the degree and order n and m increase, we probably have a large value for this polynomial P and M. And because it is a very large number, these coefficients sort of blow up in their magnitude because they have a lot of things going on for them. So there is a very big precision problem that comes in. And to overcome the precision problem, what we do is we actually normalize them. There's a big normalization program that goes with them. And if you are more interested in that, I can show you, or probably James trained some of you as to how to do the normalized coefficients. So the data then is stored in terms of the normalized coefficients, and because of the normalization, naturally the higher coefficients have a much smaller value. And because they automatically have a smaller value, when they get multiplied by 1 over r to the power of n, it also becomes, it's a product of two small numbers. So it becomes a very interesting numerical analysis problem. And of course, there is an uncertainty of these coefficients because these are actually measured empirical data. So evaluating them also becomes a problem. So let us say I have to run a 1200 by 1200 model, and then I find that that is not enough, and I suddenly have to increase to 1250, but by 1250 I have to add more terms. It's a very hard problem because I have to recompute all the elements, summation of all of them. So there is a lot of work in that, and of course, people have worked on that problem. So in Professor Schutz at UT Austin worked very hard on how to economize the evaluations of these coefficients. And there are several software programs now, thanks to them and thanks to Gottlieb, who also worked at Johnson Space Center, to efficiently evaluate some of these coefficients. And of course, those coefficients have different meaning. Some of these are called zonals, and zonals basically are like this. They basically measure, they're sort of like sines and cosines, but mapped on a sphere. So this zonals and sectorals are like sines and cosines. Some of them are latitudinal, some of them are purely longitudinal, and then some of them have a mixture of both, like a checkerboard, and those are called decimals. And each of them have their own significance in participation. And of course, as the number increases, the number of these partitions, like the orange ring, the type elements, how many layers in the onion, all those kind of things increase as you go along. And luckily, Earth is an oblate spheroid, so the second term has a much higher value than all the other terms. So we can do a lot of interesting work. However, Moon doesn't have the same advantage, so you cannot really pick one set of one particular model against another particular model. And by the way, this particular structure of composite functions and reducing the problem into unknown coefficients is not new. And we frequently go through this type of analysis, even if you're using some radial basis functions to approximate unknown physics, or if you're using neural networks which have even more hidden parameters, or if you're using Gaussians or other kernels, this is a standard regression problem. However, the key point that is different in gravity is that as we go along, the acceleration causes some of these elements to be changing in time. So this epsilon is a time varying function, and so is that. So that's sort of what. So what we have done recently is, if you have a model, and that can be a functional representation like this, or different, we can also accommodate or adjust our formulation to look at different functions. How do you, based on the errors, how do you choose which is a good model? And that's what is an optimal model order in this discussion. So what we then say is, we basically do error propagation using the first order statistics associated with the approximate, and then sort of set a threshold beyond which you are not really getting any benefit, beyond which the error propagation can be completely attributed to numerical precision issues. So for example, in this problem, you can kind of see that at 130, 140, you get law of diminishing returns when you say, let us say, talking about position error of 10 to the minus 10 kilometers does not really make sense when the uncertainty of the position is only 7 digits. Then basically beyond this, it doesn't really make any sense to close essentially. So in other words, if for more practical applications, the errors should be roughly the same order of magnitude as the uncertainty of the errors. And anything beyond that, you're basically asking too much, and you make a decision, engineering decision, on what is a desired precision, and you stop right there in this problem. In this case, this is all James McElreath's work. I'm just explaining. In this case, it is 152 seems to be a machine precision. Beyond that, you can really not do better, because It's just numerical precision is not accurate, propagate the errors. And we find that the first time it goes below this index goes below -2, we can basically address or declare that the model order 132 is reasonable. And if you want to further be economical, you can even go all the way to 10 to the 0, which gives us parity meaning any error is equal to the covariance of the error caused by the uncertainty in the coefficient. That gives you 90-90 is an even better agreement, or depending on whatever your application demands, you can slide that and then get a better optimal model. Although this is shown for this problem, we can actually develop algorithms for any other description you may have to apply this kind of a study. It is just an error budget calculation study. In this chart, we have done that, and we have done that for various altitudes, eccentricities, and types of orbits. And we show that as the eccentricity and altitude increases, the optimal model order is reduced. So you can kind of see if the eccentricity is large and we are flying at a very low altitude, you need a very high model order of 120. But as you go higher and higher away from the planetary surface, it starts behaving like a point mass, and its mass distribution effect is not that predominant. However, that behavior is not as systematic as in the case of the orientation parameters. So inclination and right ascension of the ascending node, there are pockets of the field that need very high order, and some of them you can actually see that they're roughly the same. 52 versus 58 is not going to break the bank in terms of model order. You can actually repeat this for various altitudes at different regimes, and now you kind of see a pattern. And interestingly, this pattern is correlated to the mass distribution of the moon. So you can kind of see that the order is lesser in the center, and then it is actually we need very high order models for motions about the South Pole, because the South Pole is fairly dimpled with a lot of large valleys. And also the back side of the moon is also not as regular as the front side of the moon. So you can kind of see that moon is sort of obliquely shaped because it has been helping us. It has been serving as an umbrella, taking a lot of gravitational impact on the rare side, which we don't see. And you can kind of see that in the data. Data is sometimes very useful and illuminating for those kind of studies. If we want to plot the evolution of position and velocity uncertainties, they grow like this. They start from 0, but because of the coefficients, this is, I think, 120 by 120 model of the lunar harmonics, they grow to over 2 days, they grow to half a meter, and over for the velocity, they grow all the way to 0.25 millimeters per second. This is interesting because the accuracy of a Doppler range finder for a two-tone ranging is usually of the order of 5 centimeters per second, or 1 centimeter per second, you can say. But for displacement, it is actually worse than the accuracy of the sensors is in fact 1 or 2 centimeters. So you can kind of see that here the impact of the coefficients is worse on the displacement errors, but the velocity errors are actually pretty better behaved in terms of estimation. So those are sort of some considerations that we have to pay attention to in choosing an optimal model order. It's really up to the user. What are you trying to do? If you're trying to infer and recover some maneuvers that you have performed, then we need that kind of accuracy. We need the model accuracy to not compete with measurement accuracy in order to make those kind of trade-offs in the choice of model. Just to recall where the moon is actually, of course, although we were very close to the moon earlier, moon is actually at an inclined orbit. And then, the Earth's equatorial plane is also inclined. So actually the moon, with respect to ecliptic, is only 5 degrees. With respect to Earth's equator, is fairly far away. So you have to really, that's why it looks so different. And of course, moon is not at a circular orbit, it is at an eccentricity of 0.05. And it has its own synodic period. And then there are certain long-term variations of the moon. It regresses to one revolution in 18 years and then progresses. The argument of periapse changes in about a decade and so on and so forth. About roughly 400,000 kilometers away, and so on. And that's what makes a lot of other things challenging. So if you want to really know where moon is, we don't really do any analytical models for the moon. It's all data-based. So there is an observatory which is called Apollo. It's called the Apache Point Observatory, and they basically track reflectors that have been placed on the moon. And based on that data, we sort of measure where the moon is relative to the Earth. And because those reflectors are actually placed only on one side of the moon, the center of mass of the moon is actually uncertain. I don't know how you know that. So if they have a long-term tracking of that data, so the physical librations of the moon actually trace this pattern of a long period, short period, but then there is a long period variation of where the moon is and so on. Then Earth also migrates, and this is the Earth migration data. So you can see Earth's migration also is about 20 meters, plus minus 10 meters, and plus minus 10 meters in X and Y, polar X and Y. So if you add that to the location, the moon uncertainty of about 20 to 30 meters in the center of mass of the moon with respect to the Earth, we basically usually are dealing with like a 50-meter error in where the moon is in absolute inertial space. So it's always it's an erroneous thing. And of course, between two data sets, and this is an evidence of things like experimental data. So if you look at Grail data set, Grail is like Gray's equivalent for moon. Even the equatorial radius, which is 1728 kilometers, is the equatorial radius of the moon. It is different in number from the previous data set. The Lunar Reconnaissance Orbiter LRO has also a model. That model has 1714 or something like that. It's a different model. Even the mean equatorial radius is not the same. So it's very important to sort of look at those kind of uncertainties when you're dealing with data. And this is an interesting example of geodesy to the moon. One interesting thing is, of course, going to the moon is great and all that, but it will be interesting to also know where the moon is accurately to further localize ourselves with respect to the moon. I have a few more minutes. I can quickly show some recent interesting things that happened, and then I can take questions. Of course, this is Dick Battin. So far, all the historical data we saw was basically everybody, all the scientists were striving for a model. I want to pause here for Dick Battin because he took the model and then he imbibed the philosophy that if you see some new data that disagrees with the model prediction, you have to sort of make a decision using both aspects. In other words, there is an element of what Kalman taught us that inspired Dick to actually write the navigation system that took us to the moon and back. And that Apollo guidance and navigation system is essentially the new era where we don't have infrequent measurements. We don't have to wait like 5 weeks to see the planet again. So that is captured by Battin, and of course it is getting even better in the future in that the models don't have to have an analytical form; they can be a computer program, and that's what we have to do in a chaotic regime in the next generation. So we are going towards a different time, and as we navigate through the changes in time, it's very useful to adapt and adopt what technologies we have, and sort of still keep in mind about what elegant models can do for us, essentially. So we have every model has its place and has its utility. So, and also similarly, data has its place and utility. So we really have to pay attention and respect both aspects of it. And with this, I will stop. One of the most interesting and amazing things done by Chinese is the communication satellite they have launched with Chang'e 4. I can never say it right. Chang'e 4 has a halo orbiter communication relay satellite, and the relay satellite talks to the rover, which is exploring on the far side of the moon, which is a very interesting concept, and they have pulled it off. I hope the Artemis and other things that are coming in the future are equally exciting and equally adventurous, and we try to adapt and adopt new things and new methods in this quest to learn new things in space and also to learn from data. With that, let me stop here. I have some other things that I don't want to really dwell too much. So in conclusion, space science is data science. Sometimes clumsy, quick and dirty answers are okay. And some problems are waiting for their own Kepler and Newton, who will give us a keep it simple, stupid. That's what the KISS is. And they'll probably revive a problem and give a simple answer. In many problems, we should adapt the notion that sometimes use the tools we have and provide an answer, but wait until and let it dwell in the back of the mind and give a better answer at some point in the future. It's sort of the research outlook that we can take. And we look forward to a lot of fun things that are going to happen way back to the moon. With that, let me take questions. Yes.
With regard to the optimal model order selection, I'm assuming there's a crossover point as a function of altitude where third body perturbations start to dominate. Was that considered in the
third bodies are included in that?
I think it would be higher altitude than anything that you showed. I think the harmonics would matter considerably more for what James was looking at, but I imagine there's some threshold.
There is definitely a threshold, and I think Sandeep's graph shows that. Right, so this graph really shows it, right? So you can kind of see here for Earth and Moon, these are all the harmonics, and these are the third and fourth body. In this case, for the Earth system, for the Moon system, it is the Earth's third body and Sun is the fourth body. As the radial distance increases, their contribution suddenly shoots up, and we can kind of see that for the Earth, to body, and J2 is really, really strong. And all the others are much smaller, but all of them are very important.
Yeah, 1,000 kilometers looks like the crossover.
Yes,
I have like a two-part philosophical question.
sure.
So let's assume that in a hypothetical scenario, there is some Gen Z Kepler in making at somewhere
Yeah.
right now. So according to you, what problems related to astrodynamics are worth exploring right now? And the second part is, do you think that just by looking at the data,
Yeah.
is it possible to do similar contributions? Like we have GemSwave, we have Race, but those are technological marvels which are giving you better data.
Yeah.
And that's why we have some advancements. But without taking help of engineering, do you think that it is still possible to give something meaningful to the society?
I think there is. So let me answer that question with sort of a hypothetical answer as well. So let us say that, we have a lot of data that may be conscious or subconscious, that are curated or not curated, right? So if there is a Gen Z Kepler sitting out there, one thing that they can do is first maybe solve some historical problems, right? We have a Viking rover that's missing, right? And we don't know what happened. Maybe finding, that would be an interesting problem. Second problem is I was talking to Dr. Mekorat. He was mentioning that apparently there's a lot of data on missions that did not make it to Mars. And similarly, there are a couple of data sets. There are a few data sets for, there's the data set for Jupiter probes that are there that were successful back in the day. So I think there is still a lot to learn. Of course, there's a lot of data from failed moon missions. Right? So doing forensic reconstructions can be a very good tool to Gen Z Keplers to train themselves. They don't even need to play with fancy models because even simple models can give you good training ground. I think that's a good set of problems out there. A lot of forensic analysis papers can be written, should be written, and they are essentially fertile playgrounds, I think, is one answer. Also, similarly, using different kinds of data from, like, if there is a CubeSat mission, there was a CubeSat mission that was tweeting all the time. Oh, I'm here, I'm there, and so on and so forth. So use that data to see, to basically write an orbit termination program. And those are sort of some preparatory steps they can take and train themselves. And in the process of that, you learn a lot, right? So you work with, and of course, there's a lot of open other data sets, like the whole space catalog data set is out there. Especially thanks to Astria, thanks to UT Austin, there's a lot of open data sets that are out there. So we can use them, they can use them, and then, develop some models for known objects, for objects that have not been reported, for amateur satellite observation objects. And so on. Of course, in the process of using those data sets and going through the headaches of processing real data, we all learn. And that's essentially what we should be. The answer. An answer, of course, is the yes.
So currently, many space missions, the spacecraft captures the data, relays back to the Earth, so that like the ground team can process the data and take a decision. So do you see with more and more advancements in computing power. You see a lot of the decision making happening on board the spacecraft.
I think it's already happening, right? So all the deep space stuff is all autonomous.
Mhm.
And there's sometimes not even time to actually reply. So all these, and that actually even happened on Apollo. So if you read this paper by Dick Battin, the Apollo 8, I believe, one of the Apollo missions, JSC was worried because they lost, the probe is on the other side of the moon. So they don't have any, communication. So it has to do its own, and there is a burn that needs to happen on the other side of the moon that then, puts you using the mirror theorem, puts you back on the return on a different orbit. So those have to happen or had to happen autonomously. At that time, they were using inertial sensors to automatically know, where you are for a brief period of time. It was, I think, a period of 40 minutes. I can't remember the exact number. So for that time, they just use inertial sensors. Apparently, the JSC crew did not know that, did not know about inertial navigation, but it was just it was used on board. So because I'm fixated on an Apollo instance because we have been doing that for a long time. So most of the spacecraft, this is a very popular misconception. I'm glad you asked this question. There were a lot of other graduate students who were like, oh, we sit there, we wait, and it's not true. Most of the routine spacecraft operations are all automated. And similar to the rovers, most of the rovers are automated also. They do their exploration, they get high level commands back and forth. I think it's mostly, it's already in place. Of course, you can automate even more, and that needs more accurate localization and things like that. Yes, definitely, there is a lot of work that we can still do.
Just to follow up, like sending the telemetry is the least priority when it comes to the SOP.
Yes.
So there was one slide which talked about tracking the positions using the reflectors.
Yes.
The slide a bit mentioned about the reflectors being taken down. So I wonder, like, what's the current technology they are using to track moon positions, maybe?
So we added a few reflectors. So the original ones were placed during the Apollo times, 69 time frame. In 2010, several new reflectors were placed to improve the accuracy and also improve the range. Like most of the reflectors are, if I remember correctly, they are placed in the Apollo sites, right, which are not very far from the equator of the moon. So plus minus, like I think it would be like what 40, 50 degrees, like that. And they're not also distributed longitudinally also. So it's more focused around the central Earth Moon line and so on and so forth. So what happens is there is this telescope that with a giant big laser beam that shines a flashlight at the moon. And because these reflectors are placed, they reflect the light back, and that's how they're basically getting a range signal from them. That's essentially as simple as that. So they have been, I think now they operate, well, I can't remember, 7 or 8 of them now, or 12, I can't remember, I can't remember the numbers. I think original ones were 6. Later on, I think he upgraded now to 12. There is if you are interested, I'll send you the website that has all this data.
Sure, thank you.
Yeah, even Intuitive Machines also had one. So 2 months back, we added one closer to the coach.
Even with the bad lander, they were able to add stuff. Yes, sure.
The laser doesn't seem like a scalable mechanism for, anything besides the moon.
Yeah.
Maybe that's the next
Yes.
Gen Z Kepler.
Yes. Or place a radio type thing. Especially if we are going to how humans, we need a better localization system,
Mhm.
better coordinate system. So all of this is interesting because all the gravitational harmonics are based on a reference system. That itself is wrong, right? So that's what I'm talking about. So it is half a kilometer sort of erroneous in some sense, in some bulk measures. Which is not a small number in terms of the moon. In Earth terms, it's probably small, but in moon terms, if we don't know the origin of something that is by half a kilometer, that's not. I think it'll improve pretty soon, but we need some more work. Right. On that happy note, let me stop here. I don't see any questions online.
Thank you.
Thank you. Thank you.